Okay, we start with topology. Topology, you might think, okay, this is not necessary, but usually what the notion of continuity and the topology we have from analysis is quite enough to do almost everything. But there are things which you cannot do, because the notion of continuity we have, basically continuity and compactness, comes from Euclidean space, Rn, or the real line. And this is not enough, because there are cases where the topology that some set have is not the what we call a strong topology from norms, but from other way of defining topologies which are weaker than the strong. And so we need to handle some of these things. You will find in any place where you look, there are weak topologies and so on, weak conversions, etc. So we have to learn about this a bit at least. So I'm going to tell you something about topology. So the first thing is to define a topological space. A topological space consists of a pair, X, tau, where X is a set, any set, and tau is a collection of subset of X, some collection of subsets, satisfying the following conditions. The vacuum is in tau, and X complete is in tau. That's easy. The second condition is that if you have elements of tau and you do unions, arbitrary unions, could be infinite unions, these unions also are in tau. And if you take two elements of tau and do the what's the name of that? The intersection. The intersection is also in tau. And this is all. That seems very simple. And that defines a topological space and defines a topology for the set X. Let me give you some examples. The first is very easy. Let tau be just the vacuum and the full set. And we are going to call from now on all the elements of this, so that are subsets, the open sets. What we call open set now is just any element of tau is an open set. And so what we are saying here is that the vacuum, no set is open, the full set is open, arbitrary unions of open sets are open, finite intersection of open sets are open. So the first one is only the vacuum and X are open. So this clearly satisfies all the conditions, because these two are precisely this one. The union of them, of vacuum times X is X, so it's also there. In the intersection is a vacuum, so it's also there. So this is a very trivial topology, and it's called the indiscrete topology, because it's a topology that doesn't, for instance, if you have 2 points.
Sorry, there is a question. What do you mean by one parameter family?
That you can, this is, that you can say, let me give you an example. Suppose I have an open set that is 1 over alpha 1, and I do all the union of this over all alpha between 0 and 2, whatever, or 1 and 2. That will be a union. This is a pieces of the real line, right? That I put a parameter and then I do union of all this. But it's not easy to define these things. Really, if you look at in detail, just you can say arbitrary unions. So it's, for instance, unions of things like 1 over n, 1 for n larger than 1. All of this that you will want to have some one parameter families of continuous things also. But it's really hard to say what the one parameter families of things are really precisely mathematically. But you can do it. But it's difficult. So I don't want to get into the technical parts. From what we are going to do is just infinite many open sets. I have to allow for infinite number of unions, but only finite number of intersections. Okay? So the second example is a bit better, and say let tau be the set of all subset of X. So everything you put in, any subset you can think of, you put in tau. And this also satisfies, right? Because whatever you take, these sets are there, any union is there, any intersection is there, because all subsets are there. This is the definition of an open set. So the elements of tau are open sets by definition. There is no other notion of open set just belonging to tau. And this topology is called the discrete topology. For instance, this topology, suppose one property that I want to have is, suppose I have 1 point here and 1 point here. This is my topological space. And I want to say, okay, are there an open set that surround this one, and another this one, say this is the 1, and this is the 2, and this is O1, and this is O2, and I want O1 intersection O2 equals to the vacuum. Can you do that? Clearly in this topology you cannot, because the only sets are X and the vacuum, and the only set that contains this point is X, and the only set that contains this point is X, so X intersection with X is X. So we cannot separate points with this topology. On the other hand, with this topology, if I have 2 points, then simply I take the open sets that are just So I have this point and this point. I just take the open set that is precisely this value and this other value, this other point. And then the open sets are clearly the intersection is 0, so every point can be separated. Every set of different points can be separated. So, but let's go to some more natural topology. Oh. I lose my text. Okay, here it is. Let's make an example that is more familiar to us. So let's the set X be the real numbers, R, and let tau be equals to O, a subset of R, such that if R belongs to O, then there exists O, there exists epsilon, sorry. Epsilon larger than 0, such that for all R primes minus R less than epsilon, then R prime also belongs to O. So in other words, we will say some set is open if around any point I can find an interval of length to epsilon, which is completely contained in O. This is my O. This one. Of course, O can be this piece plus this other piece, etc. But every time I am inside an O and I take a point, there is a whole interval which is epsilon interval which is inside O. And that is also a topology. So let's examine this in detail. Okay, clearly the vacuum belongs because there is no point, so this is clearly. And the whole line is also there because all the R primes are in there. So one is satisfied. Now we have to look at arbitrary unions. And suppose now that we have some R which is in some arbitrary union, then R belongs to some of these open sets, and therefore there will be exist an O such that for all R primes such that the distance to R is less than epsilon, these are also going to be here. But since are here, they are going to be in the union, and so they are going to be in the union. So that's it. And now we have to look at the third condition, which is a bit more difficult. It's not difficult. So let's say that R is in the intersection. Then since R is in O, there will be an epsilon such that all R prime with the distance to R less than epsilon are in O. And since R is on O prime, there will be an epsilon prime such that all r primes with distance less than epsilon prime, that also will be non-prime. So now we take the smallest one of these, and so all r prime with the epsilon, with the distance is less than epsilon prime prime, there will be in O and in O prime, and therefore there will be in the intersection. Notice that here, if we have allowed to have arbitrary intersections, we could have a infinite, say if we have infinite set of O's to do the intersection, this minimum could go to 0. So that's why we need a finite number of intersections. So this topology are the real numbers. With this topology is called the real line. So it's the usual topology. You can extend this, for instance, if you are in R2, right? The plane, you can give a topology there, and the topology is the same as before, except that now you say, okay, I will take x minus x prime plus y minus y prime less than epsilon. And these are the open sets. So the open sets here are something is open, if given a point, I can find a small triangle. Actually, remember we know that how this is, right? This is a triangle, a rhomboidal. Around each point there is a rhomboidal surface which is included in the open set. Okay? Up to there. So these are examples. This is usually the example we know and we like, but there are many others. Also, if you have a metric space that is a pair, a set, and a distance. A distance is a function that takes 2 points and give you something positive, 0 only if the points are equal. Is symmetric, so the distance from x to x prime is the same as the distance from x prime to x, and satisfy the triangle inequality, so the distance from one point, if you have 3 points, the distance between these two is less or equal than the distance going this way and then going this way. It's like the triangle, well, it's a triangular equality. Then with this metric space, anything you put here in D, you can do the same construction here, where here you, instead of having r minus I prime, you have D of r prime, and you get the same. So every metric space induces a topology. So this is a concept of inducing. In this case, you induce a topology by building these sets, building the sets in tau this way, with this condition. There are questions? Then this is some terminology that people usually, so we have to know. The complement of a set is denoted by this. OC this includes all the elements of X that are not included in O. And so we will say, for instance, that some subset is closed if its complement is open. So closed is defined as complements. A subset of n of x is called a neighborhood of x, a point, if there is an open set OX for which x belongs and is contained in it. So if we have a point x, a neighborhood of that point is something here that contains an open set. So the neighborhood could be closed, open, doesn't matter, but it has to contain an open set that contains a point. So a neighborhood of a point x could be closed, but has to contain an open. And sometimes it's nice to talk about neighborhoods because one don't have to care about where they are open, closed. We call the interior of A. We call it interior of A is the union of let's see how union of all elements containing A. These OA are open sets that are contained in A. So suppose you have this is A, you take all the open sets contained here and do the union, and this is interior. And the closure is all intersection of all closed sets containing A. So this is the other way around. You have A here, and take any closed thing that contains A, and do the intersection. And the boundary is formed by the closure of A minus the intersection. Are all points, and this is the same as the interior of A. The complement of the interior of A intersection the closure of A. Either way is the same. So you see these definitions depends on the topology and could be very different things according to the topology one is using. They are just topological definitions. They are all use open and closed things. So once you have the open, you say, okay, these sets are open, they satisfy the conditions for making a topology, then you can operate with this, whatever you take. There are topologies which are trivial and there are topologies which are difficult. Okay, another concept that is only based on topology is continuity, and this is very important. Differentiability is not a topological concept, but continuity is a topological concept. So every time you have topology, you have continuity, a definition of a notion of continuity. So this is just to remind, we have a map from a space to another. A map means that I take every point here, is sent to a point here, right? So I have have X here, and I have Y here, and I have a map. And this assigns everything here to something here. The image of the map is a set that all the X go to here, and we usually denote like this. So this is a set, is this set here. And we will say that the map is surjective, where it is surjective, if this is all the whole Y. So for every Y there is an X such that this map goes. And it's injective if phi of a point goes to the same point in the other side for different points, then X is equal to X. So we don't allow, in an injective map, we don't allow this. Go to the same point. If a map is surjective and injective, then we can define the inverse. We denote phi to the minus 1. And it's useful to introduce the preimage. We doesn't need to have an inverse, but it's just by notation that we introduce. The preimage is of a set O here. Let me write it here again. If I have a set O here, and I have a map phi, the preimage is all the X here, such that the maps go here. Okay? This notation is a bit confusing because the inverse might not exist, but the preimage always exists, because it's are all the X that goes in the O. Right? And so now we can, with this preimage, we can define continuity. We say phi from X to X is be a map between two topological space, so we need X and Y to have each one a topology. We'll say that map phi is continuous if given any open set in Y, here, this is Y, phi to the minus 1, so this in here, in X, is open. Right? So here we are looking at the topology of this and say, okay, this is an open set, so it's an element of tau Y. And when we look at the preimage of this C here is an element of tau X. Right? And this is the definition of continuity. It's very strange at the beginning, right? Because you might have thought, okay, a map phi, a continuous map continuous open sinks here to open sink here, but doesn't work like that. It's the other way around, and this is the correct one. So sometimes for C continuity you have to look at this in some strange topologies. This is a way. This definition, to use this definition. So let's see some examples. So let's get X and Y, and we put in X the topology of the discrete one. Remember, the discrete one was the one that every set was open. Right? Then every map here is continuous. because you take any open set here, whatever it is, phi minus 1 is some set in X, and since all sets are open, this is open. Right? So with this discrete topology, everything is continuous. The other extreme is also let X and Y be topologically spaces and let the topology of Y be the indiscrete one, that is only the vacuum and the whole set. Then any map between X and Y is continuous. Why is that? The only open sets in Y are the whole Y and the zero. The pre-image of the zero is 0, which is in X, whatever the topology of X is. And the pre-image of Y is X, because we have to assign to every X some point in Y. So we have that, and these two are open. So these maps are also continuous. So continuity, really what we think of continuity is very different than the continuity we are used to in many cases. So to have real nice, what we call continuous, to have more usefulness, what we have to do is to balance the topologies of X and Y. Don't go to the extremes. For instance, let's try to use our definition for the usual topologies. So let's X and Y be the real lines. And let the phi be a function that maps phi to 1 if X is larger than 0, and minus 1 if X is less than 0. So this is clearly discontinuous, right? So we should be able to show this. And so we take this interval in Y. This is the interval 1/2. Y is here, right? Because we are mapping the X into the Y. We take this interval. Right? What is the pre-image of this interval? Right, with the 0, yeah. Is this in here? All the positive numbers, so let me put in some other code. Is this line, which is clearly not open because it contains a 0. So we see here how the continuity fails, as should fail. So this is a right concept, and we will see later on. And here is a more intuitive version of continuity that we are mostly used to it. And so we are going to go through this to get some feeling. Let's say phi a map from X to Y is continuous if and only if given any point X in XY and any neighborhood M of Y of phi in Y of phi X, there exists a neighborhood N in X of X such that phi of n is contained in M. This is what we usually think of continuity. So let's draw this. So we have here x, and we have y here, and we say whatever, take any point here, this point goes with a map phi to phi x here. So this point is x, and this point is phi x. And the theorem says, okay, take any neighborhood here. Remember, a neighborhood is something of a point, mx, is a set that contains an open set inside here that contains x. Then there exists a neighborhood here of nx, of x, such that when you send all this here, let's change color. When you send this to that, this is contained here, inside this condition. This is what we want, because you want to say, okay, if something give me some neighborhood, whatever small it is, then I can find a neighborhood here so that the whole map maps this very close to the point. So you have a map, you send this point to this point, you say, if I give you a neighborhood here, I should be able to find a small neighborhood here such that all this neighborhood is inside this. And this is what we want. This is condition that you like about continuity. So let's try to prove it. And then we quit for the day. So let's start with continuous. Since this is if and only if, we start with some map that is continuous and prove the neighborhood thing, and then we go the other way around. So assume that this continues first. So take any point, and M like this, the construction of Ix. So by a definition of a neighborhood, exists an open set O in M, in Y, such that containing phi of x. So by continuity, phi minus 1 of O, this one is open. It's open set of F, and it contains x. And therefore it is a neighborhood of x. So let me draw this. Maybe here. No, let's do it again. So I have x here, the point x. I have y here, and the point phi x. And I have an m. I give an m here. And I say, okay, this is a neighborhood of phi x. So there should be an open set inside containing x, and I call it O. Then I look at the pre-image of this. The pre-image of that has to contain x, right, because phi of x is here, and it's open. So this is n equal to phi minus 1 of O. By continuity is open and contains the point, so it's a neighborhood of x. And now if I go back, so I take 5 of nx, this is just O. Which is contained in M. So this way is okay, it's easy. Continuity tells us what we like. Now we want to see the other way around. So, and now we have to suppose that given any point x and any neighborhood of m of ix, there exists a neighborhood n of x such that phi n is contained in M. This is what we assume now. So we are now in the following. Let me erase this and start again. So we start with this point, go here to phi x, and we say then that given any neighborhood of this M, there exists a neighborhood of here n such that phi of n is contained in M. Right? And so now we want to prove that phi is continuous. So now we take any open set so let's do it here. We're going to use this, but better to write it again. We have phi x here, and x here, and now we want to, no, sorry. Now what we want to show is that given any open set here, O, phi minus 1 of O, is open. Right? And what we are going to do is say, okay, if this is open, I take any point here, there is a neighborhood of that contained in O. Right? And so of this is phi x. No, I start. So I look at phi minus 1 of x. No, sorry. Let's do it, okay. I take a point here, inside this one. And what I want to show is that there is a neighborhood, an open set here, contained in phi, in this set, for every x. And then I know that it's open. So I have to prove this. So given this x, I have a phi of x here. And I can take a neighborhood of that. Right? So I can take any neighborhood of that, in particular something like this. And I know that the image phi minus 1 is I'm tired. No. Let me see how it is. So this O is a neighborhood, therefore yeah, I don't need this part here. I start with the O here, and I have the phi x inside here. And I say, okay, and I want to find that there is an open neighborhood here. And so I take this O, and I use this, right, as my M. So what we know, this O is now my M, so that there is an N here in this side, that is a neighborhood, and such that this thing is contained here, right? So given this, there is an N here, which I denote, I draw like that, such that phi of N is contained in O, which is M. And so phi of N, since it's contained in O, phi of N, not phi of N, N is contained in phi minus 1 of O, right? And so it's inside. So it's open, because every point contains a neighborhood which is completely contained in the set. I think for that, I'm using here something that I think I didn't prove here. That is the following. O is open. I think I didn't prove it. If and only if, or if given any x belonging to O, there exists a neighborhood of x contained in O. I think I didn't prove it, right? Which is this condition. So if I have an open set, this is my X, this is my open set. This open if given any point here I can find inside a neighborhood which is completely contained, an open set completely or a neighborhood completely contained. This is the same, this you can prove in general, but I think I didn't prove it. This is the same as is related to this way of getting topologies. This is the same. Says O is open if there is neighborhoods such that they are contained in the fully contained particular neighborhoods. But this you can prove this in the notes. I forgot. Maybe I will prove it tomorrow, because I think I forgot. So these theorems brings really continuity to what we use continuity for. And so tomorrow we are going to use in a more detailed way. And so for topology, we are going to discuss tomorrow finished continuity, then define compact sets, and then get together this into a couple of theorems. And then discuss Cauchy sequences and completeness. And this part is very, very important. We are going to use a lot of. So we need to know very well this. So let me close now. Questions on the other side? No? Okay, we close. This week is going to be theory, because we need to catch up with the theory and then we start numerics. But if we start now with numerics, it's too much. So I prefer to to use this week with all analytical things, and then next week we are going to do ordinary differential equations, and there we are going to do half analytical and half numerical. So we'll start with the numerical. But let me finish first with this part, so that we can then use freely all these things. And it's important, we are going to use most of the things we are learning now one way or another, so even for the numerical things.
Great, thank you.
You're welcome.